So, a formal digression on probability. That's the intent, that's the agenda, to introduce some basic terminology, some basic jargon. Although, to solve problems in probability, you need nothing. That's the rule of the game. But if I end up doing that, then you'll curse me for reasons more than one. But nevertheless, as part of a formal treatment of the business of probability, let me first introduce some basic jargon across to you. Come in, hop in, please. Quickly. So, in light of some basic jargon, you will very often encounter a terminology called a random experiment. You'll encounter what's referred to as a random experiment. So it's just an experiment whose outcomes you know of. It's just an experiment which could have had very many outcomes of which you have knowledge. That's a random experiment, right? So it's one whose outcomes are known. Right? Then we have what is referred to as, for example, very typically, tossing a coin is an experiment, rolling a dice is an experiment, and you know the outcome of each of these experiments. Tossing a coin has 2 outcomes, head and tails, and rolling a dice has 6 outcomes. You could get 1 or 2 or 3 or 4 or 5 or 6 and so on and so forth, right? So these are, in common parlance, referred to as random experiments, right? And then you have what they call a sample space. Yeah, please come in. So, collection or population of all possible outcomes is the sample space. Sample space is collection or population of the entire set of outcomes. That's the sample space. All outcomes of the experiment. That's called a sample space. Of the random experiment, that's called the sample space. There could be a manufacturing unit, right? Let's say making some nuts. There could be a manufacturing unit that could be making some nuts. Okay. And there are many nuts here. And a nut could be defective or non-defective. It could be defective or non-defective. N denotes non-defective. And G denotes defective. And you select 3 nuts. You select 3 nuts out of this. And when you select 3 nuts out of this, the members of the sample space, S, the sample space, the members of the sample space could be, that means when you're selecting 3 nuts, right? A nut selected could be defective or non-defective, right? The sample space could be, say, all non-defective, N, all defective, 2 non-defective, 1 defective, non-defective, defective, and so on and so forth. How many members in the sample space? 8. 8 because, you know, there are 3 nuts, 1, 2 and 3. This could be selected in 2 ways. This could be selected in 2 ways. This could be selected in 2 ways. 8 waves. So there would be 8 members in this sample space. There would be 8 members in this sample space. 8 elements of this sample space, right? 8 outcomes, so to say. 8 outcomes of this sample space. Or some, you know, sample space again, nothing cardinal about it. We could define the sample space, you know, how we want to define the sample space. For example, the sample space could be, you know, when we are selecting 3 nuts, then one possibility is no nut is defective. Another possibility is 1 nut is defective. Second possibility is 2 nuts are defective. Third possibility is all nuts are defective. So we could have had a sample space which could be redefined as follows. We could have had a sample space which could be defined as, well, once we have selected 3 nuts, no nut defective, that is designated by 0. 1 nut defective, 2 nuts defective, 3 nuts defective. That could also have been a sample space. For the same experiment, it depends on how we want to define the sample space. It's about how we want to define the sample space, right? So the members of the sample space could be these, or the members of the sample space could be these. No defective, 1 defective, 2 defective, 3 defective, and so on and so forth, right? Now, a subset of the sample space. This is a sample space, which is a consequence of an experiment, which is the consequence of an experiment. And a subset of the sample space is called an event. A subset of the sample space is called an event. What's an event? An event is a subset of a sample space. Subset of the sample space. Right? For example, an event could be, in this case, a situation where exactly 2 nuts are defective. Exactly 2 nuts are defective. Exactly 2 nuts are defective. So then that event would be the following. The first 2 defective, the third one non-defective, or D, ND, or NDD, or only 2 are defective, right? So this is all. This is the event in which exactly 2 are defective, right? This is an event in which exactly 2 are defective, and this very clearly is a subset of the sample space. This is an event, right? There could have been an event which says no nut is defective. No nut is defective, right? That means that event is like N, non-defective, just one member in that, which is also a subset of the sample space. An event could have had more than 1 element, or event could have had 1 element, right? An event could have been a union of several subsets of the sample space. An event could have been a union of several subsets of the sample space, or could have been just a single element of the sample space. This is just a single element of the sample space, right? This is called a simple event, and this is called a compound event. This is called a simple event, this is called a compound event, right? So far so good. So you understand what a random experiment is. You understand what sample space is, the population of the set of outcomes. You understand what an event is. You understand what an event is, which is essentially a subset of the sample space. Subset of the sample space, that's an event. And there could have been a simple event or there could have been a compound event, right? Now, and again, description of an event depends on how we want to description of the sample space could depend on, for the same experiment, we could have defined the sample space in different ways. The sample space could have been defined like this, or the sample space could have been defined like this for the experiment of picking up 3 nuts randomly from the set of from the manufacturing setup, right? Now, some more jargon. I have, so even before I add more jargon, let me define what is probability. Let me define probability in a classical sense, right? So, so if there is an experiment performed, and it produces n outcomes, that are equally likely, Out of these n outcomes that are equally likely, small n outcomes favor a certain event A. A certain event A is defined for that experiment. And out of these n equally likely outcomes, small n outcomes favor a certain event A, occurrence of a certain event A. Then we define the probability of the event A. As small n divided by capital N. We define the probability of the event A as number of favorable outcomes divided by total number of outcomes, assuming that all outcomes are equally likely. That's how we define the probability of an event A. But obviously you understand that, if I have a unbiased dice and I roll the dice, then all the 6 faces are equally likely to turn up. Consequently, the probability of getting 1 or getting 2 or getting 3, that's the same. 1 is as likely to be obtained as 2, which is as likely to be obtained as 3, and the probability of getting 1 is 1/6. Probability of getting 2 is also 1/6, and so on and so forth, right? These are equally likely events. However, I could have had a biased die. This is a die. And it could be biased. When I say biased, then all outcomes will not be equally likely. Let's say the die is created in a manner that the likelihood of getting a certain number will be proportional to that number. You know what I'm saying? The likelihood of getting a certain number on top when you roll the dice is proportional to that number. Right? That means the probability of getting 1, for example. The probability of 1, for example, if that's k, then the probability of getting 2 would be 2k. The probability of getting 3 would be 3k. 4 would be 4k. 5 would be 5k. 6 would be 6k. Yes or no? Right? However, the sum of the probabilities would be 1, because at least one of the events would have to certainly occur. So sum of these probabilities would have to be 1. That means k plus 2k plus 3k plus 4k plus 5k plus 6k would be 1. That means 3, 3, 6, 4, 10, 15, 21k equals 1. K then is 1 by 21. That means what's the probability of getting 4? 4k. That means 4 by 21. The probability of getting 6 would be 6 by 21, and so on and so forth. That's a biased die. You could have had a biased coin also, right? But one way or the other. So in which case there could be weights associated with the outcomes. They are not equally likely outcomes. There could be weights associated with the outcomes, right? Now, having said this, if I have 2 dice, unbiased, okay, dice D1, another dice D2, 2 dice, D1 and D2. All right. And this time my experiment is rolling the 2 dice simultaneously. My experiment is rolling the 2 dice simultaneously. So my experiment is simultaneously. Roll the dice simultaneously. And now, so every time I roll the dice, there would be a number that D1 would show up on top. There would be a number that D2 would show up on top, right? Based on that, for example, there could, and you know, there could be very many events. There could be very many outcomes of this rolling, right? An outcome could be, let's say, 1, 1, 1 showing on D1, 1 showing on D2, 1, 2, and so on and so forth. Realize how many outcomes are possible? 36, because 6 ways D1 would show up a number on top, 6 ways D2 would show up a number on top. Therefore, there are 36 outcomes in all. When I roll 2 dice, there are 36 equally likely outcomes. There are 36 equally likely outcomes in all, right? Now, when I roll these 2 dice, right, there could have been an event. There could have been an event in which the sum of the numbers, there could have been an event, say E1, where sum of the numbers of the 2 dice that show on top is, say, 8. That's one possible event, which is a subset of the sample space. The sample space has 36 elements, 36 outcomes, right? A subset of the sample space is, well, sum of the numbers 8, right? Another event, which is also a subset of the sample space, could be, let's say, sum of the numbers is 5. That's also a subset of the sample space. That's another possible event, right? This could happen in very many ways. This could happen in very many ways, right? However, realize that these 2 events cannot happen simultaneously. Do you realize these 2 events cannot take place simultaneously, right? I can't have E1 and E2 taking place simultaneously. That means E1 intersection E2 is a null set. Even intersection E2 is a null set. They cannot happen simultaneously. And if they cannot happen simultaneously, they are called mutually exclusive events. E1 and E2 are called mutually exclusive events. Because these two events cannot take place simultaneously, they are referred to as mutually exclusive events. Right? Now, say in a general sense, in Venn diagram notation, if this represents the sample space, so to say the universal set, right? This is set A, this is set B. This is set A and this is set B. Then, very clearly, the number of elements in A or B, from principle of inclusion exclusion, number of elements in A or B from principle of inclusion exclusion is going to be number of elements in A plus number of elements in B minus number of elements in A intersection B, right? Yes or no? Number of elements in A intersection B. Now, if A has n1 elements and if B has n2 elements and if S, the sample space, has n elements in it, if the sample space S has n elements in it, then the number of elements in A or B is going to be n1 plus n2 minus, let's say, the number of elements in A intersection B. Let me call it P. Let me call it P. P. Yes or no? Now, probability of A union B, A or B, probability of A or B is going to be number of elements in A or B divided by the total number of members in the sample space, divided by total number of members in the sample space, is going to be total number of members in A or B, which is this, n1 plus n2 minus p divided by n. Yes or no? Which is like n1 by n plus n2 by n minus p by n. Yes or no? n1 by n is P of A, probability of A. n2 by n is probability of B. And P by n is probability of A intersection B. That means that's going to be this is probability of A, this is probability of occurrence of B, this is probability of occurrence of A and B, A and B. So this is like probability of A plus probability of B minus probability of A and B. Yes or no? Right? Very clearly then, if I have, in this case, do you realize A and B are not mutually exclusive? They could occur together. In P ways, they could occur together. They are not mutually exclusive, right? So if A and B have to be mutually exclusive, this is my sample space. This is the case where A and B are mutually exclusive. This is the case where A and B are mutually exclusive. Then the probability of A or B, A occurring or B occurring, is going to be probability of A plus probability of B, and this will be 0 because they never occur together. Therefore, probability of A and B occurring together is 0. So that's going to be probability of A plus probability of B. So if A and B are two mutually exclusive events, then probability of A union B, A occurring or B occurring will only going to be the sum of the probabilities. Will only be the sum of the probabilities. Right? And sometimes, if you have to figure out whether two events are mutually exclusive or not, we use indirect means. If this condition is satisfied, you can indirectly conclude that the two events are mutually exclusive, right? If by some other means you are able to obtain these three numbers and they add up this way, then the conclusion is that A and B must be mutually exclusive events. And this you can extend to any number of events. If the probability of A1 union A2 union A3 union AN is PA1 plus PA2 plus PA3 plus PAN, they must be mutually exclusive events. They must be mutually exclusive events. They never occur together. They never occur together, right? Now, independent events. Please come in. Well, again, if I have two dice and I roll the two dice simultaneously. If I have two dice and roll the two dice simultaneously. And if A be the event of getting an even number on dice 1, on dice D1 say, and B be the event of getting an odd number on dice D2. B be the event of getting an odd number on dice D2. Do you realize that the event B occurring has nothing to do with event A occurring? Whether A occurs or not, that will not determine whether B will occur or not, right? Similarly for A, the outcome, this event A has nothing to do with the occurrence or non-occurrence of B. If two events do not depend on each other in this context, they are said to be independent events. They are said to be independent events. So in this case, A and B are independent events. Right? Now, I could have had a pack of cards, right? I could have had a pack of cards. And I pick a card, and I have 3 appearing on that card, right? And I replace that card. So say A could have been an event of getting 3 in the first draw. A could have been an event of getting 3 in the first draw in a well shuffled pack of cards. In a well shuffled pack of cards, A could have been an event of obtaining 3 in the first draw. Now, I replace that card. Whatever I've picked up, I replace that card. B is an event of getting 3 in the second draw. B is an event of getting 3 in the second draw. Now in this case, if I have replaced the first card, then the event B has nothing to do with event A. And they are independent events. They are then independent events, right? But if I have picked up the first card, first draw, and not replaced it, then event B, which is drawing 3 in the second draw, will depend on the outcome of the first draw, in which case A and B are dependent events. So you precisely understand what independent events are and what dependent events are, right? If an event A has a probability of occurrence PA, if the occurrence of event A has a probability PA, and if the occurrence of if there is another event B whose probability of occurrence is PB, if another event B has a probability of occurrence PB, and if they are independent events, then probability of A and B occurring, would be probability of A into probability of B. You can visually feel that all by yourself. If two events are independent events, then the probability of the two occurring together would be the product of their respective probabilities, right? And if I'm rolling 2 dice, first, so P1, let's say the probability of getting 2 in the first die would be 1 by 6. Probability of getting 3 in the second die would be 1 by 6. Probability of getting 2 in the first die and 3 in the second die would be 1 by 6 into 1 by 6, very clearly, right? Because they are independent events. Their simultaneous occurrence would have a probability. Which would be the product of their individual probabilities. So, and again, like I said, for mutually exclusive events, if two events A and B are independent events, then probability of A and B would be probability of A into probability of B. Conversely, if this condition is met, sometimes you would not know too much about the events, but through indirect means, if you have figured out that the probability of A and B is probability of A into probability of B, you could conclude that these events must have been independent events, right? Now, suppose there are a number of events, E1, E2, En. E1, E2, En. And if E1, same experiment, I'm performing an experiment of which these are the various events. They could be subsets of the sample space. And if I find that E1 union E2 union E3 union En produces the sample space S. That means together all these events will constitute all members of the sample space. Together all these events would constitute the complete sample space, right? That means if you have knowledge of these events, then you exactly know what all lies in the sample space, right? Then if this happens, then these events are called exhaustive events, These are called exhaustive events. Now, it is not necessary that these events be mutually exclusive. E1 intersection E3 may not be a null set, right? That's another paradigm. Mutually exhaustive does not guarantee that they have to be mutually exclusive. May or may not be, But together, they reflect the entire sample space. In which case, if an experiment is performed, one of these events will trigger. And if they are mutually exhaustive, probability of E1 plus probability of E2 plus probability of En, that would have to be 1. Because one of the events must take place. No, there is a glitch here. This will be 1. Let me tell you, I must add another fact here. This may not be 1. This will be 1 if they are not only exhaustive but they are also mutually exclusive. If they are also mutually exclusive, only then this condition will hold good. Think about it. For this condition to hold good, they have to be not just exhaustive, they have to be mutually exclusive. As well. Otherwise, this need not be 1. Think about it. Now, so you understand what exhaustive events are, you understand what independent events are, you understand what mutually exclusive events are, right? This is very commonly used jargon in probability. Now, as a student, I actually never cared about this jargon because it was never required. But nevertheless, from the point of view of exams, like board exams, where you would have to write down things more formally in as far as problems on probability is concerned, so deployment of this jargon becomes a must. You have to write things commensurate with the jargon that I'm teaching you. From the point of view of competitive exam, there was no jargon required. But for your board exams, you would need this jargon. Make sure you understand the deployment of this jargon suitably, right? Now, suppose this is a sample space S. This is a set A. This is a set B. These are two events. A and B are two events. Right? Now, like I told you, probability of A or B. I told you probability of A or B is probability of A plus probability of B minus probability of A intersection B. Right? Now we have a scenario where A prime or A bar. A prime or A bar is like an event in which A does not occur. A prime means A not occurring. A prime or A bar means A not occurring. Right? And so A and A prime This is like A occurring, this is like A not occurring. Do you realize they are mutually exclusive events? They cannot happen simultaneously. A occurring as well as not occurring cannot happen simultaneously. So they are mutually exclusive events, right? A intersection A prime will always be a null set. Will always be a null set. Exhaustive also, right? This A and the rest is all A bar, and together they constitute the sample space. Together they constitute the sample space. When we define probability of A divided by probability of A prime, probability of A divided by probability of A prime, we define as odds in favor of A. Probability of occurrence of A divided by probability of non-occurrence of A is odds in favor of A. And would you also want to believe that probability of A plus probability of A prime has to be 1? They are mutually exhaustive. They are mutually exhaustive, right? Probability of A plus probability of A prime is 1. Odds in favor of A is PA by PA prime, and PA prime by PA is called odds against A. Yes or no? How about it? Right?